you all are doing well. I, Vaishali Tyagi, welcome you all to the day two of the conference. After a successful session of day one of the conference, we will now be moving forward toward the session three of the event. May I request Professor Ashok Dey to become the session chair of the session. We have with us Professor Dr. Amit Majumdar, Chief Technology Officer, Grandwood Technologies Private Limited, New Delhi, who will address the participants. Dr. Amit Majumdar received his MTech and PhD degree from IIT Kharagpur. He brings 3 decades of product development, manufacture process development, and technological commercialization experience in the field of xerography, storage media, photovoltaic, LED, and OLED technology. He has worked extensively in the collaboration with international top-notch technology-driven companies located in Japan, Europe, and USA for enabling the manufacture of state-of-art high-tech products in India. At present, he is associated with Grandwood Technologies Private Limited as a Chief Technology Officer. Dr. Amit has also published various papers in reputed international journals. Everyone, Professor Dr. Amit Majumdar.
Uh, Very good morning to everybody.
Good morning, sir.
Uh, Good morning. I really thankful to Professor Mehra. He's not there today. Uh, Give me this particularly chance to speak to this honorable guest. And yesterday, I attended the whole session. I see that okay, explained to us in the last day. Today, what I'm going to speak today actually, I changed my little, not mind actually, little change because as I am last 30 years in mainly the technology development and defined product development. So I used to do more development and small R actually. I say that on what kind of technology trend is emerging in recent future actually and what happened in the past actually. And second aspect, what I'm going to cover that as a grant to technology, what we are doing in India actually. And that is, we are doing certain application research with collaboration of the IIT and that I explained in little details actually. So in the very first part, actually, you can see that last decades, actually, I am in the 30 years on the technology development. I have seen many times that due to the lack of innovation, that technology obsolescence is one of the biggest problems. And when the innovation is there, then technology is becoming affordable to each and everybody. So give me just one example. So last 10 years, I extensively working on the optical media, that storage media, uh, the flash drive storage media. And the technology emerged in 1996 and obsolescence started in 2010 because somehow the innovation could not take place in that way to further improvement. It goes from like CDR, DVD, Blu-ray, people started with the holographic media. But due to the lack of innovation, the 16 billion or 20 billion dollar market is becoming $2 million within 2 decades of time frame. Exactly same thing way that when we started working on the photovoltaics actually and PV, when we started working in this energy sector, and I think we had touched with the Professor Mehra for third generation solar cell, uh, it is completely reverse. So when we started 2010-11, so people have only, whenever we go for any project proposal or any management, people used to state the two things. Can you meet the dollar per watt peak? Means for generation of the 1 watt peak, the whether product cost can be less than dollar. And second thing, that is it possible to have a grid parity? That means that cost of the power from the renewable energy, whether it can achieve the target of the price of the thermal power. But most of this, I think, participant knows nowadays that within 10 years time frame, the things have changed so radically that when we talk about the dollar, today we talk about the cents, that watt peak is becoming 20 cents per watt peak. Grid parity, when the thermal power goes to 8 rupees, solar power is 2.5 rupees. So that happened only due to the huge kind of innovation happened in this particular field. And it is going to happen in the next 10 years because the world is moving in the renewable energy. That means that innovation without innovation, because I have seen that your research, I mean, that major topics is the academic research, but academic research without innovation is nothing. So innovation is
Amit sir, I think you have muted your mic.
is it visible that?
Yes, 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 sir. It is
Okay,
visible.
okay.
Thank you.
So I just looking, I mean, I'm reading some article that what will be the next 10 years, what kind of technology trend is emerging.
Amit sir, you're not audible, sir.
No, slide is visible? No.
Yes, slides are not visible, sir. You,
Just, sorry, I missed what happened. It's okay now?
uh, yes, sir. Yes, sir.
Okay. So just one report actually, whoever the researchers, whoever the student, they should read this report. This is the recent report by UNCTAD based on the studies. They say that what kind of digital actually technology is coming in the next 10 years and what will be the market share. So, I mean, it's moved to a like a, I mean, I need not to explain all those technologies. So there are 11 or 12 technologies which is coming already there and coming into the future. That is like gene editing, nanotechnology, blockchain, 5G, 3D printing, robotics, big data, solar PV, and drones. So that technology is moving to like a $350 billion to $3.2 billion trillion. So this is a recent trend. I think next 10 years will the world will decide actually that what is our lifestyle and what kind of technology is coming up. From this slide, we can understand that market cap is going billion to almost $3.2 trillion. Now, look into that, what kind of paper or other things is getting published actually in this particular technology. So already in the last 5 years, so these are the patent number that publication in frontier technology is artificial intelligence, robotics, nanotechnology, and this is the number of patents in the frontier technology happening in the next 10 years actually. So like it is going from 450,000 kind of number of patents applied for the AI, robotics, nanotechnology, big data, IoT, 3D printing. So these are the technologies. So whatever the recent trend of the research, what we are doing right now, it should be aligned with the what kind of technology is coming in the near future. Now, looking into that another data, when I can see actually from published by one of the so this is also one of the report I see the IBF that India is almost fifth placing the fifth position in the R&D spending. So in 2020, they spent almost $96 billion in the R&D in Indian research. And this is the fifth rank in the world actually. But when we talk about that innovations, we are the 45th rank. So that's message just I want to leave, that when we are spending almost the rank in the fifth in the worldwide R&D, but in terms of innovation, we are the rank in the 45th. So why this gap? Basically, innovation, because whatever the research we do, unless it is implemented or it is available for the mass users, then that cannot be called as innovation, where everybody should work that how our researchers and how these our universities can do a value creation out of their research. And to create a value, I think one of the very critical things that there should be strong participation in the industry, because academic institute has their own limitation. They have a very good knowledge base, they have a very good R&D mind, but for the application or realization those research into the product, we need collaboration of the on the industry and make a bigger program. Under this bigger program, somebody can have a different kind of research and then create the value and have more innovation on that. So that's the message I want to give in the recent trend in this particular R&D. So the innovation is more, I mean, one of the critical things for the creation of the value. Now, my second topics actually, I'm going to tell that what we are doing as a Grantwood company. So Grantwood Technologies, this is a startup company, and we have this Grantwood Technologies management. They have a very core knowledge in the display. With the IIT Chennai, Madras, we are doing many things, but one of the critical things that we are trying to establish a display technology leadership in India. So why we are doing, what is the reason for display technology? So let me say that for everybody's understanding, basically what is display? The displays are, I mean, everybody knows it, but just to set that tone right, I say that it is the windows of digital world data. And in the digital world, data is a first created, transmitted, processed, stored, and finally visualized in human readable from using the display. As the digitization is becoming very prominent in all the fields, so that display is becoming very, very important, particularly all the IoT devices, social media, artificial intelligence, and the requirement of the display is regularly changing. Now, data emerges from this digital highway into our physical world through displays, and display-centric products are today, everybody know, one of the major display-centric products is a smartphone, tablets, notebook, monitors, television, smartwatches, VR Air, handsets, automobile display cluster, all those things. Now, looking into that India perspective, today that there are maybe billions of mobile users, and the government of India and each mobile have a display. And if somebody look into the costing part, that display components cost us to 15 to 20% of the total bill of material cost. And that gives a huge kind of import bill to the government of India. As a result, government of India is trying or entrusted us to how to get the display business in India. Unfortunately, we don't have neither LCD or LED and other manufacturing. Now, generally, displays are two types actually broadly. One is called LED display. People say LCD display. The actual is the only one kind, that's a LCD. If the backlight is, replaced by the LED, then it is called LED display, otherwise LCD display. And there's another display called OLED display, that is the organic light emitting diode, which is the latest display started there. So basically in the display component, there is a thin film transistor blackpen and coated with certain material. In case of OLED, In case of OLED, in case of LED, it have a backlight, then TFT backplane, and liquid crystals, and some of the color filters, and you get the LCD display panel. Now, if you see that market scenario today, because obviously it is academic research, but what I was trying to bring this point that unless there's a market pull, innovation may not happen because then it is not sustainable actually. So today display industry is reached almost 107 billion US dollar, and it is going to $226 billion. And as we discussed that we have a two kind of display mainly. One is the LCD display, another is the OLED display. OLED display based on the organics. So slowly you can see that this is the movement of the OLED display. So this is slowly that OLED display in 2026, it will convert from to LCD to OLED by like almost 80%. Today, whatever we buy a high-end mobile phone, like above 30,000, they are all OLED display. And in case of and the LCD displays are the low-end phone actually. So that's the market trends. That is the smartphone market is now, larger, and consumers are now prefer more AMOLED display. So basically it's a bendable, foldable, those kind of flexibility in the AMOLED display, and those flexibility is not there in case of LCD display. So just let me explain that a little bit. What is AMOLED display or OLED display? Basically, it has a organic light-emitting diode. This is a current-driven light-emitting device and compromising mainly the functional layers. And this is they are called active matrix OLED because each pixels you can actually control by using the thin film transistors. And normal layer we have a flexible, then we have anode, hole injection layer, hole transport layer, and then emissive layer, hole blocking layer, electron transport layer, electron trapping layer, and then you can get the light emissions actually. So this is as per the AMOLED display structure, and these are the benefit over the LCD versus OLED because it gives the good image quality because it can reproduce very nice black color. True black color is not possible in the LCD, but it is possible in the OLED. It can have a faster refresh. It does not need any backlight and wider color range and lower power consumptions. And moreover, you can make it flexible actually. It can bend, it can flexible. So these are the advantage of AMOLED technology. And that is the reason the market share is slowly increasing in case of AMOLED display. Now, these are the supply chain. I'm just skipping the slide for the time being because when you have a display unit in this company, you need other industries too. Actually, you need like a sputtering target. You need the light management frames. You need the fine metal mask. So many things to make a device out of this display. Now, what we are doing in the AMOLED display project at IIT Madras. So these are the project entrusted by the government of India, particularly Ministry of Electronics, METI, Tata, and DRDO. And this the market size as discussed is SCO. So government of India entrusted this project to have this grant with the grant to technology. So this is one of the projects that I want to showcase that it is a private and government partnership project actually. So grant to technology is giving the technology to IIT to develop a next generation of display. And as a CTO, I am controlling that product. And there are IIT from side, there are 5 principal investigators are there. A dedicated team is working in this particular display unit and make India a display-centric research and innovation at that particular center. So these are the overall project things that we do that phase 1, that development R&D, then we do the pilot plant, and this is the deployment of the commercial production That is the total motto of this center. And Government of India is going to announce it as a center of excellence for the display. Now, how this is a integrated project, because this display project is not a simple just manufacturing a display, because it need the one of the things that LTPS TFT blackplane, that is low temperature polysilicon TFT blackplane. Unfortunately, India does not have that capability for any kind of fab industry. So because this is one of the bottlenecks, that's why we have to partner with some of the Asian company like Taiwan or somewhere else actually to get this LTPS TFT, because this LTFT TFT substrate is always customized for your product and product design. So a lot of design rules and design inputs are there depending on the what kind of display you are making actually. So in IIT, we are doing that, have a OLED deposition and OLED encapsulations and trying to do, and when you make a display, it does not work automatically. You need a lot of electronics, a lot of drives. So that's another project is going on, that how we can design those drivers and this for the display. So then we ultimately go for a panel design. So in this project, there are two aspects. One is the product development, and second are the underlying technology development or R&D. So this is the, fine metal mask. Then we have a process I explained to the CSS and CSS pastel process, how all those R&D. So there are group of students, actually group of professors, they are taking a particular research project based on this to basically support this bigger activity in IIT. These models we have, always when this any private company goes to the IIT, it is very difficult. There are a lot of issues that how we can conjugate, because government does not give the money to. So basically, Grant Wood Technology, what we are doing, we have a licensed background IP. We have a very some intellectual property, and we have a joint development partner. And when it creates the new IP, intellectual property, the IIT, it will be jointly shared actually. So all the background and IP for the Grant Wood and IIT jointly start doing, making a commercial product actually. So commercialization activity will be run by the Grant Wood, and the basic research under the guidance of Grant Wood Technology will develop the product. In this particular product, because now question is that, already this display technology is there. There are Samsung, LG, they are making a lot of AMOLED device. Then what is the innovation in this particular product? So we have a technology differentiation that is called CSS process. We call the closed space sublimation. Normally, this any display technology, we do the linear evaporation process. Here we are going to do a closed space sublimation process. And if we are successful to do or demonstrate the CSS process, then entry barrier to having the factory, because normally any display industry needed billions of dollars. So we can make a micro factories using those particular technique, and we can have a, we can have a manufacturing capability. Plus, if we have our own IP, then that will actually, there'll be no entry barrier for the Indian company in this particular business. So that's why we are doing a technology that is a CSS AMOLED process, and Grant Wood Technology has certain patent for this unique process. Now, going back that what is the CSS process we are doing actually, what is the advantage? So normally this, when organic films are getting deposited, it is linear evaporation. It is a continuous evaporate and the glass moves and we get. So what we are doing that we have first we deposit a small film on the glass, and then through optical radiation part, we actually, this OLED materials, that thin film will transfer to the product substrate. The product substrate means TFT. And these steps, so two-step process, one the organic materials reusable, and then step 2, those organic materials are delivered to the product substrate from transfer substrate. And these are all kind of vacuum printing. I cannot disclose the full because it's a lot of patent and a lot of other technicalities are there. So normally this process have a much faster, a 100% organic material, because one of the cost factor for the organic materials which is very expensive. Here we can material utilization move from 30 to 90%. As a result, the actual display cost will go down. And another part actually in the display industry, it is called fine metal mask. to make the pixels, actually, to design the pixels. This is the maskless process, actually. And so that will have some business impact, like it can have a much faster cycle time, it can have a zero particle environment. So those are and we can, basically for any kind of red, green, blue, RGB color device, we can actually reduce the material cost. So these are the key process of the Pascal process, actually. So we have like a TFT substrate, then we deposit one kind of OLED materials, then we do the maskless patterning through CSS process, and this is OLED 2, and this is cathode, and this model. Okay, that's the process we are following, and I mean we have now developing the Pascal substrate, which can have a two heating zone. One is the cooler zone, another is the heater zone. So we can say the low reflective and high reflective zone, and we heat it, so there will be a difference in the temperature between the two spots. One is that we are talking the micron level actually heating, I mean thermal difference, and that gives the very selective deposition to making the pixel patterns. So this is the concept of equipment is already there. We have our own design of the equipment. So here, these are the organic chamber. This is a mask. This is the cathode chamber, and this is a loading chamber of the substrate. So everything processed under 10 to the minus vacuum level. This is a transfer chamber where substrate can invert, then go to that our new process. This is Pascal stock chamber, that what we talk the CSS process. It will the patterning, then it will go to the transfer, and then ultimately, and then it goes for the bonding chamber. So this is a real picture of our AMOLED equipment in the R&D facility. We are making a prototype facility here, and this is, I mean, due to this pandemic, it is little delayed, but during the pandemic also somehow we managed to get the equipment installed, commission. Now we are doing all the kind of experiment. And this is a picture for using those bonding part, and this is the experiment we are doing. The project is managed a little bit different way, because it is typical the way actually the private, you can see that we have, I mean, we are making a, like, what is the key performance index. So the project is subdivided in 7 small projects, and who will responsible, and what kind of I mean target we have every quarter, and what percentage we are actually achieving, and then based on that it will be scorecard will be followed. It is typically, I mean, a culture of private company, but frankly speaking, today government of India may be also asking this kind of progress report every month actually. So we have a agenda how we can do the technology demonstrations. Then we go for how we are going to do the technology deployment. Then this is basically how we can do the center of excellence, because we have to spread this technology. I have a lot of partners on that. Then we have a strategic and commercial, how we can do the strategic and commercial, because generate all the IPs actually, like we have like around 22 IPs we have to develop in the next 1 year, and then how we can have a strategic partner for that particular project. And so this is overall technology roadmap actually. We 2009 we have a prototype facility, state of art technology, to understand that okay, we can actually develop AMOLED, and then we are looking for the CSS process, and then we go for 2020 flexible, and 2020 we can do. So this is basically R&D part, technology required, R&D funding, then we have pilot material, and simultaneously we are working with some of the Indian company where we can develop the OLED materials actually at inside actually, so that we have a very make up India kind of things, that where we can actually have a technology doing everything. So I can see another 1 minute, so let me do. So this is basically our big picture. We have to a roadmap for display industry creation in India, and that's the way actually, I mean, we have a understanding that we have a SKF Display Corporation that they'll do the design, TFT backplane, panel manufacturing. And India, I mean, India means we will do the AMOLED design, panel manufacturing, and module assembly. and hopefully by next 2 to 3 years time frame, we are able to do uh, basically Atmanirbhar India actually, where we can make a display. And just for government of India already announced that expression of India for the display, and some of the companies already applying. So we are looking to it, and uh, they are giving lot of, I mean, they are already declared. We have published a big report where for as a expert that different kind of scheme that production linked incentive scheme and other things, how the government can encourage to have this industry in India. So I think we thankful to METI because they are helping us a lot to basically encourage to the product development and R&D and technology development with IIT Chennai. Thank you very much, actually.
Thank you so much, sir. Please accept our token of appreciation from the team CIR.
Thank you.
Now I request Dr. Prabhakar Singh, Professor and former Head Department of Physics, IIT BHU, to deliver his talk. Dr. Prabhakar got his PhD in Natural Sciences from Institute of Physical Chemistry, University of Münster, Germany, and his MTech from School of Material Science and Technology, Institute of Technology, Banaras Hindu University. Currently, he is working as a professor in Department of Physics, IIT BHU. His areas of research are ion conducting glasses, materials for fuel cells, solar cells, electronic chemics, condensed matter physics, and renewable energy sources. Sir, all yours.
So, thank you, Vaishali. Am I audible?
Yes, sir, you're audible. Yes.
Yeah,
Namaskar.
thank you. Namaskar, sir. Namaskar. So, first of
Namaskar.
all, I'm
Very
ah,
happy to see you. Namaskar.
namaste, sir. So, I'm indeed thankful to Professor R.M. Mehra, who encouraged me to give a talk in this conference, and Dr. Shweta also. This is, I think, I'm just going to presentation mode. I hope that everything will be working. So, entire screen, let us see. It is not coming. Wait a minute, just a minute. I don't know. Okay, so is my screen visible?
Yes, sir, it is visible.
The band gap engineering, it is visible?
Yes, sir.
Yeah, good. Thank you. So now, is it in full screen?
Yes, sir, it is visible and it is in full screen.
Oh, that's good. Thank you. Thank you, Vaishali ji.
Thank you.
So, uh, uh, so I'm giving a talk, just a general idea how band gap engineering can influence our whole life, actually, the surroundings and everything, and the materials, how we can make a band gap, and all these things I will talk about. And before that, we should just, for the physics students, I would like to just introduce what is band gap basically. So what is band gap engineering? No? So before that, we go to the band gap engineering. We should understand also the origin of the band gap theory, which is you know that if you are having a gaseous molecules, are the molecules or the atoms which are separated far away. Of course, if you calculate or if you take the spectra, you measure the spectra, you will find the line spectrum. But when in solids, actually, the atoms are very, very closed, and you can see these, this separation is about A. It may be in angstrom, of course. So you see that when the atoms are very close, the outermost electrons, basically, they are not separated. They are basically shared by those atoms also. And then when you make a quantum mechanics calculation, you will find that they will be separated in a group of energies, and each group of energy is separated by very small distances. And they are forced to do that because of the Pauli exclusion principle. You know that Pauli exclusion principle tells us that no two electrons can sit in a single energy state, and therefore the energy states are splitted, and they are formed in a group. And the groups of the different orbitals are separated by some energy difference, and that is known as the energy gap. And this is the reference is given solid state physics. And then if you try to classify what the solids on the basis of band theory, you know that very easily you can distinguish, because in the metals there is no band gap between the conduction band and the valence band, and they are overlapping. So you can see this picture where there is overlapping of the Fermi level, and the Fermi level merged into the conduction band. And here in a semiconductor, there is, of course, there is a gap between the conduction band and the valence band. And when you have if you go to the insulators, this gap is wide, very wide, and more than 3 electron volts. So this is a kind of band gap. Now, why band gap is very important, and how we can create and how we can do the engineering, then we will see in next slides. You see that to manipulate the band gap of any material is very essential. And why it is essential? Because we need to have their application in a different scenario, in a different physical applications. So for that, we need to manipulate, or you can say that we can tune the band gap. Rather, manipulation, we can say that tune the band gap according to our need. And then you can see that this is the review articles. They are increasing very fast in the just manipulating the band gap and everything. So you can check it with this. Now, how this is the review article. The band gap, which is tuned and aligned in a different range. Actually, suppose, for example, I take these are the different range: infrared region, visible region, ultraviolet region, and of course the microwave and the terahertz regime. And these are the different materials. For example, let us say MOO3, molybdenum oxide. This can be tuned within the range of 2.8 to 3 electron volt. Similarly, if you take MnO2 randomly, then it is 2.2, and their application is from visible to the ultraviolet. And you know that any material, when the light or any form of energy falls, the atoms and molecules, they are going to the next energy state, and they are returning back. And correspondingly, they can emit energy in terms of the electromagnetic wave. These are the electromagnetic wave spectrum, which is shown in corresponding to different energy level, energy band gap. So they are basically electronic band gap engineering, where we make manipulation of the energy band gap of material based on different, of course, the techniques. And we can also make the photonic band gap. The photonic band gap, they are also the similar form of the periodic optical nanostructure that affects the motion of the electromagnetic wave. and some of the crystals, they do not allow a particular band or a particular range of wavelength or frequency to go through, and that is creating a kind of band gap. And you can see, just I put a picture, this is butterfly, and of course they are having different colors and they are reflected back and reaching to our eyes. And then we can see and we can say that these they are containing the periodic arrangement of the crystals on their wings, and of course they are in a two-dimensional form. They are very, very thin actually. So this is the basically the band gap engineering for the photonic material, for the photonic band gap. This is the photonic band, and this is in our group. We are working on this. Dr. Jha is who is the basically the research associate who is working on this material. So you see that this is basically a calculation, which is finite element modeling simulation we did, and we found for different thickness. You see, this is for the TiO2 and the graphene. So we have plotted this omega with the different thickness. We took for two thicknesses just for demonstration, which is 10 nanometer and 50 nanometer, and we calculated this difference. And this is done for the difference of the material. You can see that these are the
Okay, excellent. Thank you very much. Okay, if you can see my screen and if you can hear me properly, I can start now. Would someone
Yes,
please confirm?
yes, sir. You're audible as well as your slides are visible, sir. You can continue.
Okay, now the topic of my talk is rather is a patchwork. I'm going to give you a glimpse of how electromagnetic waves can be of interest to us in our daily lives. It's not going to be very technical. If you're hoping it's going to be a lot of mathematics, you'll be disappointed. So I'll remain on the surface, but I'll be happy to take any specific questions. Now, let me jump into the deep end. Here, what you're seeing is a radar. Now, this radar is not meant for detecting aircraft or locating aircraft, but it is meant for recording echoes from clouds. So here you can see the antenna dish, which reflects any electromagnetic energy trained on this dish. The signal goes out, etc., and something comes back from a scatterer. A scatterer means a discontinuity, such as a cloud. So this is an example of an electromagnetic wave application, radars, and radars occur in almost every walk of life. Um, Now, this is just a brief example. It's what we call uh, a C-band radar. C-band simply means it is a 5.5 gigahertz signal. 1 gigahertz, as you might recall, 1,000 megahertz. And so this is a C-band radar ideally suited for recording scattering from clouds or rain or weather. So this is one example of how electromagnetic waves, particularly microwaves, may be of use to us in our daily lives. Yet another example comes from the area of satellites. Now, you might know ISRO in India is very, very active in in making satellites and observing the Earth surface up from the space. Now, the best place to observe Earth is not sit in a jeep or you go cross country and track the geology and the geophysics of the region. um, Instead, a much better way of observing the Earth is to have a position high up in space and look downwards and see how you can cover a larger area than you would be able to cover with a motor car or a vehicle, just driving cross country. Um, Now, these sensors, these satellites, usually carry a radar of some kind. Now, the radar is actually hidden here. There's this flat plate. Do you see my cursor? I hope you see it. This flat plate here below. You're right. This is actually the antenna. It's a printed antenna, or well, not quite printed. It's a slotted waveguide antenna. You punch holes in waveguides, and out of these holes in the waveguides, your electromagnetic signal comes out. And due to the location of these holes, what happens is you have constructive and destructive interference of the signals creeping out of these little holes. And you design the position of the holes in such a way, as a bit like the my predecessor talked about lattices, crystal lattices. Um, the lattice is designed in such a way that you have constructive interference in the forward direction, and you can have a beam of electromagnetic waves. So, the wave physics has commonalities in different areas, ranging from if you like, from band gap to all the way down to simple radio science. It's a fascinating thing that waves, physics of waves, binds us together. Now, this this radar, this satellite radar, um, works because most of the electromagnetic waves can can penetrate through the cloud and yet reach the ground and illuminate the ground. And following illumination of the ground, you will have reflections coming back to your antenna, which picks it up and maps the region which you have illuminated. So this is a very, very interesting application, which is going to play a major role in the next few years. Now, this slide is a very generic slide. You know, you see it all over. On the horizontal axis, you see the frequency or the wavelength, whatever you wish. And on the y-axis, you see the attenuation in decibels per kilometer. And if you were to look at this graph, you'll see that there is very low attenuation in the microwave range, right? From 10 to the 8 hertz to 10 to the 10 hertz. And so this window of low attenuation, right, enables the application of diverse devices, which you might like to deploy rather than employ, deploy on the Earth's surface. So this is one picture which you might like to keep in mind as to why we use microwaves so much when it comes to using electromagnetic sensors for observing the Earth. Now, I have great temptation to digress a little. There is a frequency here, and that frequency is about 3 gigahertz, somewhere here. The attenuation is low, most definitely, but at 3 gigahertz, what happens is your water molecules, wherever they might be present, if you were to expose them to 3 gigahertz signal, they absorb a lot of energy, right, due to a resonance effect. And this is how your microwave oven works. Yeah. So whenever you put anything in your microwave oven, right, your food gets hot. Your nice, I don't know what you like, to eat, biryani, or ranging from biryani to anything, whichever, something nice, something profusely Indian would be nice, but it should have some water in it. Should have water molecules in it, and if you have water molecules in it, yeah, you can heat it up now, because your 3 gigahertz signal would show resonance absorption, and that's why your microwave oven will not heat up your glass. It will heat up the food, but not the glass container in which you might have placed your food to make it hot. Right, that was a mild digression there.
Sorry to interrupt you, Professor Madhu. Can you start your presenting again? Something went wrong.
Sorry, I couldn't hear you too well. Could you please repeat yourself?
Yeah, what I'm saying that it looks like we have lost your presentation. So can you share it again? Can you share your screen again?
Oh, have you lost my presentation?
Yeah, something went wrong.
Sir, I think it has been minimized or some other issues has come because it is coming on a small screen. So if you can please share it again.
Okay, I'll do so. I'll switch it off. Just a moment, please. All right. Yeah. Okay. This is my screen. I'll go back here and also, so I should be completely gone, I guess. And
Yes, sir.
I'll now try to ein Fenster ganzes Bildschirm. And I am. Do you see my presentation now?
Yeah, it's coming.
Yes, sir, it's coming.
Now it's okay. You can proceed.
So do I restart? Okay.
No. You can start from the point where you left because
Okay. Right. I hope you can hear me properly. Now, what are the main features which we have to take into account when electromagnetic wave-based sensors are employed? Well, a lot of these electromagnetic waves, as they crisscross through the Earth atmosphere, they are affected. And they're affected by, for example, the atmospheric gases, water vapor, which might be present in the air. And they definitely will be affected by what we call hydrometeors. Hydrometeors is a very fancy word for raindrops, snow crystals, hail, whatever, anything made up of water are known as hydrometeors. Naturally, clouds, and last but not least, the ionosphere. And for completeness, I have included the term multipath effects. And multipath effects are simply sort of electromagnetic waves reflected from different scatterers, regrouping at some stage. This phenomenon carries the name multipath effect. So as a result of all these different media, and all the interactions I briefly alluded to, what happens is your electromagnetic waves will get attenuated, all electromagnetic, but waves not only lose their amplitude, but they also may experience a phase shift in the sense that the amount of electrical distance covered by your electromagnetic wave will depend on the medium through which they are traveling. Depolarization. Now, what is that? Now, that means that the state of polarization of your electron.
I'm extremely sorry for disturbing you again. Sir, your presentation has been unpinned. Can you just pin it? There's one,
wait a minute.
yeah.
Wait a minute. I think there is somebody named Pooja Kumari. Actually,
Yes, sir. We have removed her. We have removed her.
Okay.
Just Madhu sir, can you just pin your presentation? It will be on a maximizing screen. If you can see a
Spin.
small icon of a pin on your screen.
I see a small icon. So you mean presentation mode?
No. You have to just double
Rajiv
click.
sir, you can do that.
All right, let me try that. I'll try this presentation mode. Is that any better?
No, sir, not yet. Rajiv sir, just pin the presentation.
Sorry, I didn't.
Yeah,
I didn't.
no, it's okay.
You said spin.
No, it's okay.
Pin,
Pin.
sir.
Now it's done, I think. Correct?
Not yet, sir.
Could you please repeat your message?
Sir, actually, I am asking to pin your presentation. There is one
pin,
icon.
to
Yes, sir.
pin it.
Yes.
All right. Okay, I got you now. Let me try this. I'll do the presentation and then pin. How do I pin it?
The symbol of the pin, if you see.
Symbol, or I think I'll have to go back to the
Sir?
presentation.
Right click on that window. If there is a pin is there available, then click on that.
I'll just see. Yeah, I think there's something here. Just a moment. Ausblenden. Try immer noch klicken Sie die Präsentation fortzusetzen oder zu pin. I saw something to this effect. Pin it. CC. Oh boy.
Maybe you can restart the sharing. That will.
First you stop the sharing, then reshare it, sir.
Yeah.
Okay. Yeah. All right. Bildschirm wird eingeblendet. And is it better now?
Yes, better.
Yes,
Sir.
Yes,
Now
much
full
better.
screen. F5,
Oh.
sir, on that presentation.
Yeah.
Full screen.
Okay. I'm so happy it's worked out. Hope it stays like that. I don't know what I did, but it seems to be working. Right. So without further ado, let me progress into the talk. Now, what you're seeing here is a radar image from a C-band radar, which I showed you in the very beginning. Now, this shows you that on the horizontal axis here, you're seeing the range. And in the vertical axis, you are seeing you are seeing the height. And your radar is placed at the origin, and the antenna is looking at, is trained to look, towards the cursor here, and then the antenna orientation is changed in elevation. So as a result, your antenna beam, cuts out a scan through the cloud, and you can see that the cloud has been illuminated by electromagnetic waves, and whatever echoes it generates, you can use those echoes for charting out, for mapping the structure of the rain cloud. Now, such radars are not only used on the ground, but also used in aircraft. And this is a very typical rain, which you might see in the European part of the world. In India, you will see it too. I remember from my Indian days that you will see such rain structures if you start getting closer to the Himalayan range. You will have a rain of this type, in which you have sort of low-level rain, but which lingers on for a long time. And now let's look at this little rain cloud. What is happening here? Now, what is happening here is made visible through another picture of the same cloud. But this picture was generated by looking at the electromagnetic scattering along two polarizations, one the horizontal and the other one the vertical. And then we took the ratio of the two echoes. And engineers, as usual, or physicists, for that sake, they very often use decibels to express numbers which span a large dynamic range. So decibels are a very good way of expressing numbers which vary enormously over your range of interest. And now looking at this quantity known as differential reflectivity, which is the reflectance of electromagnetic waves at two polarizations, and thereupon you take the ratio of the two reflectances, one at horizontal, one at vertical. You take the ratio and you generate a quantity known as differential reflectivity. And differential reflectivity, if you were to study this signature, it reveals fascinating things. For example, what you might be seeing here, these purple colored structures here, they are snow particles, and snow particles scatter more on horizontal polarization than on the vertical polarization. And these snow particles, as they fall from a higher elevation to a lower elevation, they start conglomerating and become snowflakes. And snowflakes do not have a specific shape. They have no favored orientation. So as a result of that, the scattering anisotropy is lost. So snowflakes, once they are generated, they give you low differential reflectivity. And this color, white color here, where my cursor is jumping back and forth, has a 0 dB differential reflectivity. 0 dB means the ratio is 1. The ratio is 1. It means horizontal and vertical scattering are the same magnitude. And yeah, sure enough, so you have landed in this region of snowflakes, and when these snowflakes start to melt, they become, what happens is they collapse, and due to the surface tension, the collapsed snowflake becomes a water droplet, and the water droplet, due to the effect of gravity, becomes like a flat structure. So many people think that raindrop has the shape of wie heißt das? The shape of a pear. Pear? I know the Indian word for it, nashpati. Yeah, something like this. But no, that's what you see in advertisements. The shape of a raindrop is actually like a flattened bun, which you get when you have your soup. You get a little bun, and along with it. So that bunny shape is the shape of a raindrop, and not the tear drop, or the nashpati shape. I hope you know this word, which I know, nashpati. I hope they still call it nashpati. And so that's the shape of. So nashpati is not the shape of raindrop, I hasten to add. It is more like a bun, yeah? And it comes as a bit of a surprise, doesn't it? And that's why you see higher differential reflectivities when the snowflakes are converted into raindrops. And as the raindrops fall, they conglomerate, they become large. And once they become large, they become so large that the surface tension can't hold the raindrop. And the raindrop disintegrates into smaller raindrops. And smaller raindrops are less oblate. They're less oblate than the initial raindrops. And that's why the differential reflectivity falls again. Now, why am I telling you all this? The reason I'm telling you all this is you can use these features from simple physics in order to classify your cloud. And that's what you see here. You can classify your cloud into regions of ice crystals, melting band, region of rain. You may say, why is it of interest to me? The answer is in aviation safety, this plays a very, very big role. Now, whether your aircraft flies through rain, or whether it flies through the ice crystals, or whether it flies through the melting band, it has an immense effect. I will show you one picture rather rapidly. Here is, here is a cloud. Again, what you see is um, as a cloud in which you have a radar picture of a cloud. And what do you see here? The cloud, rain cloud, is rising up to 12 kilometers in height, right? And there's no melting band. There is just intense rain with very large raindrops. And these are columns of convection. And as a result, if an aircraft were to fly through this, then the passengers and the pilot would be very, 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 very uncomfortable. As a matter of fact, it would be life-threatening to fly through such a cloud. So the pilots can circumvent this danger by flying around the cloud, providing their radar is able to pick this up. Some of you might recall there was a very tragic air crash of Air France when off the Brazilian coast. And what had happened was the aircraft flew into such a cloud here, like this. This is not the same cloud, I hasten to add. And the electromagnetic signals got attenuated terribly. See, here you're seeing some attenuation effect. And the pilots thought that there is no reflection. So they thought the cloud is safe. And they started to fly through a very dangerous cloud. And the reason it was not scattering back was the electromagnetic waves got absorbed by the water and there were no reflections. And the pilot were not, the chief pilot was having his dinner, sadly. And the young trainee pilot who was flying did not realize that attenuation in radars could be something which he has to take into account. And as a result, due to lack of training, pilot made an error and he flew through a very, very, very notorious cloud, which got the aircraft down, sadly. So that's an example of radars being used in studying the Earth atmosphere and in aviation safety. I'd like to show you some another picture of weather radar application. Now here in the middle of the crosswire, I hope you can still hear me. I hope I'm still there. I hope I'm coming through. Would someone please briefly confirm?
Yeah, we can hear you.
Thank you very much indeed. Now here in where you see the middle, the origin of this crosswire, this is the city of Oberpfaffenhofen near Munich. This is, and what you see here are the Alps, where all these skiing, these winter ski resorts are located. You probably see them on the television occasionally, I guess. But I suppose in India, you have much better places in the Himalayas. But these European Alps, they're not very high. No. Compared to the Indian mountains, they're very, very modest. But they're very snow-rich, like the Himalayas, no doubt. And these mountains are beautiful when it comes to snow, when it comes to skiing, when it comes to winter sports, but they're a pain in the neck when it comes to weather prediction. Why? Because you can't tell them apart. The scattering which you're seeing here from the mountains may be confused, may be taken for rain cloud. And this is exactly what's happening here. You see in the picture above, you have a rain cloud, this diffuse cloud system, diffuse colors, and these diffuse colors are superimposed on the mountains, the German Alps, the Austrian Alps. This must be Austria here, and so this is the Austrian and German Alps, and and as I said, your rain, as it spans the field in which the Alps are located, the radar operator can't say whether the high scattering is coming from the ground or from the rain. Now, many of you might think it might be easy to subtract, just take away the ground scattering and leave the scattering from rain. It's not that simple. The reason is once the ground gets wet, it starts to behave itself like rain. And so it gets a bit complicated. So we have to figure out a better method of separating rain from mountains, right? Now, how can that happen? Now, you'll see in the picture below, the rain has disappeared, only the mountains are left. In the above picture, both were present. Mind you, the data is from the same situation, but so what did we do? How did we do magic in order to remove the rain, and just make the mountains visible, or vice versa, make rain visible and mountains invisible? Well, the answer is we change the polarization. If you use circular polarization, it turns out that the raindrops are polarization sensitive, and the ground, the mountains are not polarization sensitive. And it turns out that the raindrops are such that you will have no signal, very little signal coming back if you were to illuminate the raindrops with circular polarization. Exactly. So if you were to send out a right circular polarization, and once it hits a raindrop, then what comes back is left circular polarization. So it means you're not getting signal back into the channel in which you sent your signal out. And as a result, you lose your signal from the rain part. And once you lose your signal from the rain part, what's left? You are left with the mountains. So this is a very interesting application of polarization, and so polarization serving the mankind, if you like. I'd like to jump to the last application. I'm getting close to the end of my talk, I guess. This is something known as synthetic aperture radar. I know ISRO in India is highly active in the area. Now, what's happened? What's a synthetic aperture radar? Some of you might know it. You have a very, very ordinary radar, a very cheap, simple radar. Yeah. As a matter of fact, a very homebrew radar will do good, will work. But you can make this cheap, simple radar into a very powerful radar, providing you were to make your radar fly on an aircraft, and you make your radar look towards the ground. So two things: you move your radar and you train your beam towards the ground. Now, what does that do? Now, it simply means you take a simple radar, you move it from one point to the other along the flight path, as if you're taking photograph pictures of the same object from different positions. And by doing this, you can synthesize a very high resolution image. Again, it is the periodicity which matters here, and my predecessor gave a very interesting talk on band gap, and he was alluding to the periodicity time and time again. And the same type of effect is happening here. You are generating a constructive interference by taking coherently measured signals from different positions. And if you add them constructively, you can create a high resolution image with a high signal to noise ratio, with a high amplitude. So that is the trick which lies behind synthetic aperture radars. And here is a wonderful picture. There is a synthetic aperture radar. Now this is a picture over the Soviet, not Soviet Union, sorry. It's a picture over Russia, right? um, and the and in this synthetic aperture radar measured scattering from the ground, so you were able to chart out the ground. But there's something else, a part of the ground signal which we were trying to measure in order to figure out the terrain and map uh, the land surface we were looking. A part of it was blackened out due to attenuation from the clouds here, which you can see. And one of my PhD students, to whom I'm very grateful for his work, Dr. Dunkelmeyer, Dr. Dunkelmeyer analyzed this phenomenon, and he predicted how this signal from the synthetic aperture radar would lose its strength in illuminating the ground. And he was actually, he went on to use this negative effect in order to get information on the cloud. And so useful was his work that he got the Best Paper Award for IEEE. So this young man was able to predict more than we thought we could get out of the data. So that's an example for research students. If you have data which has very funny effects, yeah, hey, don't throw it away straight away. Don't chuck it in the bin straight away. Maybe you want to take a closer look at it and see why the data is bad. And once you know the data is not corrupt or there's no artifact in it, and if the data is showing some irregular behavior, hey, then you are lucky. You have hit the jackpot. You might find something interesting, and that's exactly what Dr. Dunkelmeyer did. He realized that this blackening is due to a cloud here, and this cloud, he was able to work out properties of the clouds as a result of that. Now, I'll just show you one last picture, and then I'll try to conclude for you, because I think I've lost a lot of time. And now, what's happening here? Here again, you're seeing a cloud. And this cloud, you have a signature of some kind. And now you're wondering, what is this radar signature telling us about the cloud? Now, if you look at the colors say go along this path. You start with blue color, you hit green, and then it becomes red. And if you look at the scale below, yeah, blue is minus 41 degrees, and green is something like minus 35 degrees, and the reddish color is something like 25 degrees. So we're talking of angles. So what is changing here? We're talking about a phase shift. And why is the phase shift occurring as you penetrate into a cloud? The answer is the horizontally polarized waves and vertically polarized waves travel at the two polarizations of light or electromagnetic waves do not propagate with the same velocity. That is to say, the material has different refractive indices along the two polarizations. And as a result of that, what happens is there is the phases of the two waves horizontally polarized waves and vertically polarized waves start to drift away from each other, and you start picking up a differential phase. And this differential phase is fascinating. Why is it fascinating? The reason is it will not be affected by attenuation. You are using forward propagation, so you're using forward scattering in order to obtain information on the cloud. So using methods such as these, they will be able to improve the the application of weather radars to a new level in which the radar operator has not to be worried about attenuation, like the pilots of Air France aeroplane. If they had had a signature of this type, they would have been able to see the cloud all the way through. And this phenomenon uh, is something which I think you will see in the next generation of radars all over the world. Now, I think I'm reaching somewhat towards the end of my talk. I think I've completed my time, taken more time than I should have taken. So I'll abruptly close at this point of time, and I'll be happy to take up any questions or suggestions which you might have. So with these words, I'd like to close the talk and pass the mic back to the conference leadership.
Thank you so much, sir. It was a delight to hear you and see your presentation. Please accept our token of appreciation from Team CIR.
Thank you. Thank you very much.
Thank you, sir. Now I request Dr. Professor Mainuddin, ex-DRDO scientist professor and former head of Department of Electronics and Communication Engineering, Jamia Millia Islamia, New Delhi, to deliver his talk.
Thank you, ma'am. Good morning. Let me share my presentation first. Am I audible?
Yeah. We can hear you.
Okay.
बताओ एक्स डीआरडीओ साइंटिस्ट प्रेजेंटेशन अपनी प्रेजेंट कर रहा है रिगार्डिंग लेजर एंड इट्स एप्लीकेशन.
I'm audible now?
Yes, yes.
Okay.
We can see
First
your
of all,
presentation also now.
okay. Thank you, sir. First of all, I would like to
Sir, you're not audible.
I'm thankful to Professor Mehra and Dr. Baral for giving me an opportunity to speak in the National Conference on recent trends in academic research. My topic is latest trends in lasers and its application. So let me see my bandwidth. I'm switching off my video. You know, laser is considered as one of the top technological achievement of 20th century. It is a fantastic tool that plays an important
Professor Mainuddin, can you unmute yourself? Looks like you are muted.
I don't know. It is getting muted itself. Okay.
Okay.
Now it is clear.
Yes.
Okay. So laser has touched upon almost every sphere of our life. Even in beauty parlor, you will find role of laser. So during last decade, several Nobel Prizes are backed by laser or laser-related technologies. Keeping in view the importance of the light, year 2015 was celebrated as International Year of Light by United Nations. So even in this conference, the keynote talk and invited talk one is related to single photon emitter. So this shows how important is light technology. So the content of my talk uh, is a brief history and evolution of laser, laser fundamental, classification, and finally laser applications with emphasis to defense. I try to make it general so to see the heterogeneity of the audience. So coming to the history of the laser, in 1917, Albert Einstein developed the concept of stimulated emission, which is phenomena used in laser. Later on, Towns and Shallows developed first device based on stimulated emission, which is named as MASER. MASER means microwave amplification by stimulated emission of radiation. In 1958, the same researchers suggested that stimulated concept can also be extended to optical region. And it is the Bosov and Prokhorov of Lebedev Institute, Moscow, that extended measure to optical regime, and they won Nobel Prize in 1964 for this work. In 1960, T. Mann demonstrated first Ruby laser, and in 1962, a group of researchers worked on semiconductor laser diodes. Another important research that was demonstration of first optical fiber, which opened up a new field of optical fiber communication. Now, high speed data transmission is a reality. We could enjoy this data speed because of the optical fiber communication. So, laser is nothing but it is an acronym for light amplification by stimulated emission of radiation. Laser is a device that transforms any form of energy into electromagnetic radiation.
Sorry to
The
interrupt you, Professor. Are you
Yes,
changing your slides or it's
yeah,
easier?
I'm changing my slide. Is it not changing?
Okay, now we can see it. Yeah. Thank you.
Okay, yeah. I just made it in a slideshow mode. Okay, let me take it without slideshow. Laser is a device that transform any form of energy into electromagnetic radiation. The input energy to the laser can be electromagnetic radiation, it can be electrical energy, chemical energy, even it can be mechanical energy. But output of the laser will always be electromagnetic radiation, which includes visible light also. So in next slide shows the basic mechanism behind lasing action. An atom in lower state absorbs photon and then it moves to higher energy state. The atom in excited state can decay spontaneously to lower level and emits a photon. This photon have random direction and phase. But when we use another photon to who compel this excited state atom to come down, then it will emit another photon that will be exactly same as the incoming photon. That is what is known as stimulated emission. And stimulated emission, what makes a laser different from the ordinary light? So let us see what is the uniqueness in laser light. So laser is highly monochromatic light. That means monochromatic means it will emit only single wavelength, and ideally it should emit single wavelength. Then it is highly directional. That means it will not spread much during propagation. And laser light is highly coherent. That means all the waves are in same phase. So in next slide, I try to show another property, that is the brightness of the laser. You can compare from the table that even 1 milliwatt helium neon laser is 100 times brighter than the sun. So this is how bright is laser. As far as the directionality is concerned, low divergence or high beam quality results in highly directional beam that can travel a longer distance and can be focused to a circular spot that will be useful in defense application. So coming to the different kind of lasers, laser covers all the wavelength starting from UV to visible to IR region. Excimer lasers are available in the range of 190 nanometer to 350 nanometer. In visible range, important lasers available are ruby, helium neon, copper vapor, etc. Near infrared lasers have got attention due to its several advantages, which I will cover in subsequent slides. The important near infrared lasers are Nd:YAG, chemical oxygen iodine laser, that is coil, then HFDF, etc. We also have mid-infrared lasers like CO2 laser that emit at 10.6 micron. So different applications require different parameters, lasing parameters. The important parameters of lasers include wavelength, line width, beam quality, power, etc. So if we are looking for a laser for optical fiber communication, then I'm interested in a wavelength of, let us say, 1.55 micron, which is a low wavelength in optical fiber. Similarly, if I want to use a laser for industrial purpose, then I'm interested in a power level of around 1 to 10 kilowatt kind of things. And for defense application, power requirement will be hundreds of kilowatts. So there is no laser which can fulfill all the needs. So different laser technologies have been developed over the years. So coming to the classification of the lasers, we can classify laser in a number of ways. One of the way is based on the lasing material. We can have solid state laser, we can have liquid laser, and we can have gas laser. Solid state lasers are the lasers in which lasing medium is solid, like ruby laser, Nd:YAG laser, ND glass laser. But in solid state laser, due to the poor heat dissipation, sometimes solid rod gets damaged. So people are interested in liquid laser because of this. In circulation mode, we can have better heat dissipation capabilities of the liquid medium. So dye lasers are known since long, but nowadays recent trend is people are developing different types of liquid lasers for different high power application. In gas laser, different gas lasers are CO2 laser, CO laser, nitrogen laser, copper vapor laser, etc. Similarly, we have chemical lasers. Chemical lasers use chemical energy for population inversion and like that. We can also classify laser based on the power level. As far as the power level is concerned, then any laser with 0.3 microwatt comes in the class 1 laser. And this kind of lasers are used in CD player and scanner. Class 2 laser includes the power level of 1 milliwatt, and these lasers are normally being used for alignment purposes. Class 3A lasers have a power level of 5 milliwatt, and they are hazardous only for intra-beam viewing. Similarly, we have class 3B lasers. They are moderate power lasers of around 500 milliwatt. Any laser which is greater or equal to 500 milliwatt is termed as high power laser, and they have if you look into the lasers directly or indirectly, they are hazardous to you. So when you are handling high power lasers, you should be very careful. Handling of, normally people keep high power laser beam height above the human height for sake of safety purposes. So now let me come to the another part of the talk, that is application of the laser. So I'll cover laser application in industry, in medicine, in test and measurement equipments or scientific experiments, laser in communication, and finally it is laser in defense application. As far as the industrial application are concerned, the evolution of industrial laser is shown in this slide. CO2 laser have been known to us since long, and other industrial lasers are like Nd:YAG, excimer lasers are also popular. For industrial applications, typically 1 to 10 kilowatt power levels are required. Then let me go to the next slide, which will show the different lasers available for industrial application along with their power levels. If you look carefully into this slide, you will find there is a new entrant like fiber laser, which has been used for industrial application. Nowadays, 10 kilowatt single mode fiber lasers are reality, which are very much useful in industrial application. Similarly, chemical oxygen iodine laser is also very popular for industrial application. We'll see some of the application of coil in a subsequent slide. So laser can be used in cutting of the metal or welding of the metal. As far as the laser cutting is concerned, previous methods of punch press require the punch press kind of things provide you less precision, and there are safety issues in manual operation. So it is the laser which will give you very fine finish. You can cut the material using laser beam. So how does it work? The laser beam is focused onto the material, and then sufficient power density is generated to melt the material. The molten material will reflect back your laser beam. Then how to avoid this problem? Then what is done? Then assisted nitrogen gas is normally used to remove the molten material from the surface. So with the help of laser, you can achieve excellent accuracy and precision. And it is safe to operate because you are operating a machine, laser based machine remotely, and there is no direct human contact, so it will be safe to operate. Next application, it is very interesting application which is demonstrated by Japanese. They use laser for remote dismantling and disposal of obsolete nuclear reactor. So in 1998, Japanese have used 10 kilowatt chemical oxygen iodine laser. Normally we call it coil. Coil is nothing but it is chemical oxygen iodine laser. And that 10 kilowatt laser is transported to the nuclear site with the help of an optical fiber. And now it is the robotic arm that dismantle the obsolete nuclear reactor for its safe disposal. So this is one of the application which is used to cut the metal. Next application is laser welding. So welding of different metals can be done with the help of laser. You will find a very precise welding, and you will find its application in a lot of automobile industries. Laser has find application in medicine. So lasers are used in surgery. For soft tissues clinical application, CO2, Nd:YAG, and diode lasers are being used. Whereas for hard tissue clinical application, erbium lasers are the best suited choice. These are used for removal of impacted tooth under bone or bone grafting, etc. All of you are aware of LASIK. LASIK is nothing but it is a laser based equipment which will give you freedom from cataract problems. So how does it work? No, the tiny flap of outer cornea is folded back, and then laser removes the tissue from the remaining cornea to change its shape, and then finally flap of outer cornea is reattached. So what kind of laser is useful for it? Normally lower wavelength laser is preferred, and lower level wavelength means we are interested in UV range. So excimer laser is the best suited laser for this application due to several advantages. Now next application is laser is used for tattoo removal. What is done in this case? Laser breaks the pigments in tattoo into tiny particles, and then it is the body immune system then attack and destroy them. And important lasers which are being used in this application are ruby, Nd:YAG, and alexandrite. So as far as the laser application in scientific experiments is concerned, laser has found a number of application. I'll show you one of the application, that is gas concentration measurement of any species. I'll take an example of chemical oxygen iodine laser. See, chemical oxygen iodine laser is a laser in which iodine is a lasing medium. It's a high flowing gas medium laser in which iodine is the lasing medium. Both lake and axis of the iodine will degrade laser performance. Then there is a need to precisely measure iodine flow rates or iodine concentration in the laser cavity. But problem is that since it involves high speed gases, you cannot put external sensor inside the flow. So you have to have a method which is non-contact type. So in this case, we can use optical technique. You know, iodine molecule has a peak absorption at 499 nanometer. So in this setup, a laser beam is passed through the medium and signal is detected at the other end. In case of there is no iodine, you will get a signal. Once iodine starts flowing through the line, then molecules will absorb the signal and you will get a dip in the detector. So by using Beer-Lambert law, you can estimate the number density or concentration of the iodine molecule. This is how we can use optical technique for gas concentration measurement. This is one of the system which I developed during my tenure at DRDO for chemical oxygen iodine laser. So another application is if you can use laser for if you visit any mall or grocery shop, you will find laser based barcode scanner which are used for inventory and pricing information. It is possible to quickly obtain data on both at the same time. Lasers are also used, in another application like roughness testing of the surface. So roughness is an imperfection on the surface of the material. One can use backscatter signal, and then you can you can estimate the roughness number of the surface. You have find speed measurement device with the police person. So sometimes they can use Doppler shift based laser speed measurement system, and they will find over speeding vehicle. So this is also one of the application of laser based device. Now coming to the communication field, nowadays it is possible to transmit signal with the speed of gigabit per second. That is commonly available nowadays. So this is possible because of the advent of optical communication. Optical fiber communication offers a lot of advantage over the RF communication, like it has very high bandwidth. It cannot be intercepted by unauthorized person easily. It does not have any EMI EMC problem. And however, installation of optical fiber cable is tedious and costly affair. The first commercial installation of optical fiber system was completed in 1977 by Bell Lab. In this case, how does it work? Laser acts as a carrier of my signal. My signal can be audio or video or can be text. So it is modulated and transmitted over the fiber, and then it is demodulated at the other end. The important wavelengths which are useful for communication purposes, for optical fiber communication purposes, is 1.55 micrometer. This is the wavelength which offers minimum attenuation in optical fiber. Similarly, we can use 1.310 micrometer wavelength, which exhibit low dispersion. So this is how laser can be used in optical communication. You have find application of laser in laser printer to find a good quality print. I will not spend much time here. And similarly, you have an application of laser in CD players. So see, CD-ROM uses a semiconductor laser to read the binary information from the disk, and without laser, there will be no CD player. Now, coming to my last part of the talk, that is defense application of laser. In defense, laser can be used as a tool or as a weapon. So if you use laser as a tool, you can have an application like laser rangefinder or target designator or many other applications like that. Or you can use laser as a countermeasure for countermeasure purposes. So as a weapon, you can use laser as a directed energy weapon. For laser to be used as a DEW, it should be able to produce very high power so that you can destroy the target. It should have a very large operation time so that sufficient power can be reached to the target. It should have high influence on the target, and in battlefield scenario, electrical power is a problem. You cannot find electrical power easily there. So you should have a laser system that should operate with minimum electrical power requirement. What is the solution for DEW lasers? You have an option like HFDF lasers. You can use chemical oxygen iodine laser, or you can use CO2 GDL. All four lasers already showed their capability to use as a DEW application. Because of the reason that these lasers does not operate on electricity. The only electricity requirement is just for supply of the sensors and actuators. Lasing action is due to the either mechanical energy or it is the chemical energy. As far as the HF and DF laser is concerned, these lasers are highly toxic, so people don't use these kind of lasers nowadays. CO2 GDL is a very bulky system. It operates at a very high temperature and high pressure, and it is a noisy system. So that is why CO2 GDL is now obsolete technology. So the only if you are looking for a megawatt class kind of laser, it is the chemical oxygen iodine laser. Recent trend is to use coil for megawatt class of lasers. Lot of research has been done, and people are still doing lot many things to realize a system which can qualify for high power laser category. Other lasers are also available, which are also competitor for these technologies like solid state lasers and fiber lasers. But solid state laser and fiber lasers these lasers are not able to exceed power level more than 100 kilowatt by combining several modules. Still, lot of research is being done in this field to get megawatt class kind of lasers for defense application. So let me start with the laser as a tool in defense. One of the application I have shown here is laser target designator. What is done in this case? You have heard the word laser guided bomb or laser guided missile. How does it work? What is done then? The target is you shine the target with the laser. Now your missile or your laser guided bomb will be following this this laser, and now it will be destroying the target. So you have already seen or heard about the laser guided bomb or laser guided missile. They work in the same way. You can use same laser to countermeasure this kind of threat. What is done if you are detecting laser threat? I'll go to back to this slide again. If you are detecting any laser threat by using some detector or laser threat warner, then how you can deceive the guided bomb. How will you do it? Either you can generate high power laser and you can transmit back to the this weapon side, then its detector will get saturated. This is one of the way you can deceive. You can use countermeasure. Or another way is you can generate a smoke screen so that target the weapon can be deceived. This is how people are using laser for pinpoint destruction of the target and its deception. As a weapon, laser can be used as a weapon. It is a very old technology. Light was used as a weapon even in 212 BC. Archimedes used sunlight to destroy a boat. So The same experiment was reproduced by MIT in 2009. What they did, they collected sunlight, and the light is reflected from a couple of mirrors, and they demonstrated that boat is destroyed by the sunlight. So this is how the laser was used in old days to destroy the target. Laser. So nowadays, people are using laser as a weapon. Why do we use laser as a weapon? We have, number of advantages. One of the advantages is this, that laser operates at the speed of light. That means enemy will not have, any reaction time to this weapon. So that's why this is one of the advantages of DEW. Another advantage is that, see, if you fire at laser, whether it hits the target or it does not hit the target, your millions of dollars have gone. So, but in case of laser-based weapon, laser equipment is always with you. You can you can do multiple firing, and the multiple firing with the cost effectiveness is possible with the DW based equipment. And one more important advantage of directed energy weapon is that it has zero gravity effect. So these kind of system can be employed in space kind of application. So next slide, the previous speaker showed one of the slide in which he showed atmospheric transmission window for microwave. But we are interested in, transmission window of atmosphere for optical signals. If you look at this graph, you will find that 0.8 to 1.5 micrometer is the wavelength at which you will get around 70% of atmospheric transmission. And lower the wavelength, more will be the photon energy. E is equal to SC by lambda. So lower wavelength will have better energy per photon, and lower wavelength will also have laser better laser material interaction, and it will have a smaller optic size, and fiber compatibility is also there. So because of all these advantages, people are working on developing DEW lasers in this range, only 0.8 to 1.5 micron. So this is the justification how people are working or interested in this range only. So in next slide, I will try to show you some of the international, scenario for using laser as a weapon. In order to fulfill demand for DEW application, latest trends in source selection is fiber and liquid lasers. For tactical application like engagement of UAV up to 8 to 10 kilometer with the power level of 100 kilowatt. So 100 kilowatt power has already been demonstrated by these two lasers like fiber and liquid laser. But if we are looking for destroying the missile at enemy territory during its boost stage itself, then we are looking for strategic applications in which I need a megawatt class of laser which can destroy the target with the range of, let us say, 150 to 500 kilometer range. And for this kind of power level, today we have only one option, that is chemical oxygen iodine laser. Other lasers of megawatt class were also developed, but due to the toxicity of the chemicals which are being used in that those lasers, people did not continue that research that I discussed in my previous part of the talk. So let me see what kind of laser system have already been demonstrated by international community. Yes, one of the system is airborne laser, ABL. ABL, this laser has been demonstrated by US in 2010. What they did, they assembled 200 kilowatt coil modules. 6 modules were combined together, and they are mounted on a Boeing 747 aircraft. and aim was to destroy the missile during their cruise phase. So they successfully demonstrated, destruction of the target at 150 kilometer. The another important laser that is, reported in the literature, that is advanced tactical lasers, ATL. ATL also utilizes coil chemical oxygen iodide laser of around 200 kilowatt, and they mounted this laser on C-130 aircraft, and successfully this laser demonstrated destruction of the target at around 8 kilometers. So if you look at international military scenario, coil is the option which is already reached to a stage that different weapon systems have been demonstrated, and different countries are working towards development of this laser. However, since the involvement of chemicals in this laser, it is difficult to handle several chemicals, but they are not as dangerous as HFDF. But still, people want to develop a laser system based on solid state technology or fiber. So a lot of work is being done in fiber lasers or solid state lasers. What they are trying to do, they are trying to develop a module of, let us say, 10 kilowatt modules or 20 kilowatt modules or 50 kilowatt modules. Then they will try to do beam combining so that they can reach up to the level of megawatt class of laser. But still, lot of work is to be done. It is under development stage. So future is for solid state and ABL, but for megawatt class of laser till date, coil is the only option. So to conclude my talk, I can say that laser have touched upon every sphere of our life, starting from barcode scanner to medical to industry and defense applications. So different lasers have used different platform for diverse missions. And with this, let me say thank you for patience listening. Thank you so much.
Thank you so much, sir. May I request Rajiv Kumar Srivastava, sir, session chair, to deliver the vote of thanks to our speakers?
Okay, so first of all, I want to thank Professor Madhu Chandra for his talk on usage of radars. Especially, he explained very well how this can be used to understand the cloud composition, and which can be very helpful for aviation safety. And also, he explained very well the volumetric measurements and synthetic aperture radar. Thanks a lot for this valuable presentation. Then I want to thank Professor Mainuddin for his very interesting talk on lasers. And he very nicely explained the concepts of laser and its classification. And then the best part was its application. I mean, we were all surprised to see that the laser application is applicable to our for a small task of daily lives, and also for the complex defense system. And that was really interesting. So thanks a lot, Professor Mainuddin.
Thank you, sir.
Thank you, Professor Mainuddin. Thank you.
Thank you, sir. Thank you so much, sir.
Thank you, sir. Please, Mainuddin, sir, please accept a token of appreciation from Team CIR.
Thanks a lot.
I would like to request Mehra, sir, to please conclude this conference.
Yeah, it has been a very nice experience. We organized this particular conference for the first time. I'm thankful to all the eminent speakers. I'm sure that all the participants have been enlightened. I myself have learned many things. New things were discussed. So today's speaker, Madhuji, Mainuddin, and Amitava, all are expert in their field, and we need their cooperation in future as well, their support also in future as well. And I congratulate my team who are monitoring Vaishali and her team, who are monitoring the whole system. There
Thank
was
you, sir.
absolutely no disturbance, and whenever there was some issue of presentation, Vaishali was able to solve it. So thank you very much, Vaishali, and thank
Thank
you
you, sir. Thank you, sir.
all the good wishes. And I hope the blessings of our eminent speakers will remain forever. Thank you very much. Thank you.
Thank you, sir. Rose sir, if you want to add something to it.
Rajiv ji, thank you for chairing such a wonderful session and summarizing it in a very nice way.
Thank you, sir. Thank you.
Ruth sir, if you want to add something.
Dr. Kamal Kishan Sharma has been throughout the meeting, and I will like him to share his expressions about this conference. I'll be delighted.
All right. So with this, we come to an end of the conference. We hope that you all had an insightful session in these 2 days. And on the behalf of the team CIR, I would like to thank all the speakers for giving your time and delivering such an insightful and informative session. Thank you everyone for joining us and being a patient hearing and making this conference such a big success. At the end, all the participants who will be presenting their papers, I would like to request all of them to join their respective rooms. Thank you, everyone. Thank you so much.
Ma'am, how we can get the room?
Your links must have been sent to your email ID, sir.
Thank you.
Okay. Thank you, sir. Thank you so much, everyone.
Excuse me, ma'am. Which link do we have to join for paper presentation? Hello. Yes, sir.
You get the mail for the.
I didn't receive any mail, but ma'am has right now sent me the link.
A very good morning to all of you. Hi, I am Manshi. I welcome you all in the paper presentation session at room 4 at day 2 of the conference, Recent Trends in Academic Research. Firstly, I would like to brief all of you regarding rules of this session. So each presenter will have to spend 10 minutes to present their paper, where the presenter should focus on results and conclusions of their paper, keeping in mind that the introduction part should be a little brief. So after 7 minutes, the presenter will be notified so that remaining presentation is wrapped up in the remaining 3 minutes. As the name of the presenter is announced, you have to unmute yourself and present your screen. Every other participant should keep themselves at mute for maintaining the decorum of this room. So I hope all of you must have noted the order in which you will have to present your paper. So in order to begin, I would like to begin with the first presenter, who is Manpreet Kaur, and she will be presenting the paper of the title, Simultaneous Estimation of Tramadol and Atoroxid by UV Spectrophotometer and RT-HPLC. Hi.